Okay, get to today here. All right, so on the board here I've put some information about the first, the midterm. The way I graded it, problems 1 through 12, I graded. Number 13, I counted as a bonus. Okay. The class average was a 70. The standard deviation is 19. Do y'all know what that is? Standard deviation? Yeah, pretty much. I mean, we're not going to be too statistical here, but it just tells us that the grades varied from that average pretty dramatically. So we had people above it quite a bit, people below it quite a bit. And then we had 2 A's, 2 B's, 2 C's, so only 6 people technically passed the test, and then 10 D's or F's. 101 was the highest grade, the median grade was a 66, and the low was a 21. I think that's all the data we need at this point. So what this exam was worth, 25% of your grade or something like that. So let's just, I mean, for right now, I don't want us to get, like, if you've been doing really well on your mini exams, you know, 80s, 90s, and you did poorly on this one, don't let it discourage you. You have an idea of what I would ask on a midterm now, and I have an idea of what you can do on a test like that. So, you know what I'm saying? Like, we know a little bit more about each other now, and I think we can be, you know, positive moving ahead. As long as you're doing your homework, as long as you're staying on track on your mini tests, I'd say I don't think anyone in here should bail out of this at this point, unless you've been failing your mini test too, your take-homes. So, all right. So we'll worry about grade later. All right. Let me kill at least one set of lights here. I have not posted the answers to the mini exam or the midterm. I will do that. Give me another day or two, and I'll get those out there. If you have any questions over anything on what I took off for, please just meet with me. I'll be happy to go over anything that you wish to talk about. Okay, I took the time this spring break. I had not created lecture notes for chapters 12 or 13 yet. I had little bits and pieces of things. I had a lot of the Mathematica code with the 3D visualizations already done from years ago, but I had never put the notes together really, so I did that. And I also printed them out and bound them for you. So this is just chapter 12. You'll get chapter 13 when it's time for 13, okay? So just take one of these, pass it around. You can open it up. It's sideways like this. You can put, you know, chapter 12, whatever you want on the front of this. Got any extras? Just these? You got one? Now, here's a little disclaimer. I'm going to provide these notes in PDF form also, where each page is a full page, because some of the notes are real small and they didn't come out real well because it's actually like a copy of a copy, and sometimes of a copy. It's like the third time through the machine. So just if you need to look at something and have a more clarity, just go onto Canvas and I'll put all the PDFs there so you can take a look there, all right? But this at least will help you when we're in class go through and you'll know what I'm talking about. Now, we are not doing chapter 12 today. We still have to finish chapter 11. So we have to do 11.8. Does everyone have their 11.8 notes? Hope you do. Anybody not have them? Because there might be some in that filing cabinet. I don't know. And I'm gonna shut this door a little bit. I did something. I don't know if any of you have been watching that whole thing with the plane that's missing. But it turns out that it's an interesting math problem. Well, not the whole thing, but let me. They did a little demo yesterday on one of the newscasts, and I thought it was a really cool demonstration. Made it really make sense. So I thought I would put together some code real quick and show you in class here what they're talking about. So y'all have heard that the plane can be on, like, they know it like got to some point, and then it's either like up on some arc and down on some arc, right? It either took like a left or right. That's what they're saying, right? Y'all, have y'all heard that? If you've been watching it. So basically, it took off. At some point, it turned left, and at some point, it either is up here or down here. So that's kind of like, how do they not know which way it went, right? Well, here's the explanation of how that all works out. There's the Earth. This, let's say, is the, hold on a second, why is this not? I guess I never changed that. All right, let's just say that that's the, this is an exaggeration, but there's the Earth. The blue is the range of the plane. So the plane took off from the center, took off, and it's only got so much gas, right? So it's got to land somewhere in that blue region. All right? Is that fair? Okay. Now, forget that for a second. There is a satellite sitting out in orbit, right? And this satellite can see a portion of the Earth. Now, wherever the line of sight hits tangent to the Earth, it cannot see anything over the other side of that because the Earth blocks it, right? So these are tangent lines to this, to the Earth. So everything in the red here, it's kind of hard to see, it's red, but everything in the red there is what the satellite can see. Now this is three-dimensional, right? This is three-dimensional, so the satellite can see everything in there. Well, what happened was that the engines in the plane were sending out a signal, trying to send a signal out, and the satellite was able to read that signal. And the satellite was able to measure the distance from itself to the ping, is what they're calling it. So from itself to the engine. So let's imagine that there was a ping that came from somewhere. We'll look at it from the side like this. So let's say that here's a satellite, and then there was a ping, and it can measure that distance, right? The satellite does. But because the ping came from on the Earth, it could have come from anywhere on that circle. Do y'all see my little circle here? Anywhere on that circle? Every point on that green circle is the same distance from the satellite, right? So that ping could have come from anywhere on that green. Yeah? But then if you throw in the plane, the range, God, I can't spin this frickin' thing around. There we go. If you throw the range in again, then you know that it's got to be in the blue and on the green. And they know it took off, and they know it took a left because they've got it on radar. And then at some point after that, it got a ping a certain distance from the satellites, which means it had to be on the arc, on that arc right there. So they know that it's either the arc up or the arc down. That's pretty much it. So in this class, what we could ask ourselves is, what's the equation of that green circle? Well, that would be the intersection of a sphere, right, the Earth, with the sphere centered at the satellite. Radius is that green distance, right? Imagine a sphere that comes through. If you had a sphere right here coming through here, then wouldn't where they intersect be that circle? So, you know, I did it by, you know, on paper and everything, and had Mathematica do it as just an exercise. But all it is solving two equations with three variables, and what you get is an equation in two variables, which is a circle. All right? So just kind of interesting. I was sitting there watching it, and I was like, huh, that's like a Cal 3 math sort of visualization problem. All right, let's get that out of here. What's that? What was on it? People. No. Okay, where are we at? 11.8. All right, so we're going to cover what's called Lagrange multipliers, or Lagrange's method. There's different people call it different things. I like to just call it Lagrange. Everyone kind of knows what I'm talking about when I say Lagrange. It's not Legendre. You might hear that word in mathematics and stuff. Also, Legendre is totally different. Lagrange. What this is going to allow us to do is find optimum solutions to problems. Kind of like what we were doing before, where we had a surface and we found like the max and min, those sorts of things. We're going to be able to find that sort of thing again, but it's a different method and it's really very powerful. So I already said in the previous sections we found max min, right? We could do it on implied domains or on closed bounded regions. Right, those are the two things that we could do from 11.7. Give me a function on its whole domain. I'll find its max and min by computing D, right? Figuring out saddle, local max, local min. Or give me a closed bounded region. Then I have to go along all the edges and check all the points. And so that's what we did in 11.7. The method of Lagrange multipliers in two variables. So it's actually Lagrange multipliers works for 2 variables or 3 variables or 4, 5, 6. It doesn't matter. So let's start with 2 variables. So let's say we're given a function f of xy subject to a constraint g of xy equals k. This will all come to light once I show you the visualization. But you have a function and it's constrained or restricted by some other equation. What we do is the following to find the maximum minimum values of that function f. You find all the values x, y, and lambda such that these two conditions are met. The gradient of f is equal to lambda times the gradient of g, which means that, remember, the gradient is a vector, isn't it? The gradient's a vector. So this vector, you need to figure out what x, y, and z's make this vector a scalar multiple of the gradient of g. Lambda is a constant. Constant times a vector is a scalar multiple of it. So figure out what x, y, and lambda make that true, and then also you must always be able to satisfy the constraint equation, which is this one. Then what we do is once we find x, y, and lambda, we evaluate the function at the points that we found. The largest is the max, the smallest is the min. That's the method. Now, here's a couple of things that we need to make sure we're clear on. When we say gradient of f here, since it's a function of 2 variables, remember the gradient is the partial of f with respect to x. That's the x component of the vector. And then partial of f with respect to y is the y component. We need that to be equal to lambda times the gradient of g. The only way that vectors can be equal is if their components are equal. So you set the partial of f with respect to x equal to lambda partial of g with respect to x, and that gives you this first equation, right? Then you do the same thing for the y components, and you get this equation. So we have 2 equations, right? Now, 2 equations. Then you have the second condition that the constraint must be maintained. So we have a third equation, which is good, because how many variables do we have? X, y, lambda, right? 3 variables, 3 equations. We should be able to solve it, right? Now, the way I try and do it in class, what you'll see is with the 3 equations, I like to put them in almost like columns when I'm working them out on my paper. I'll do the first equation, second equation, third equation, and then somewhere maybe in here I might reference equation 2. So I might put, and because equation 2, and everyone will know I'm talking about this equation, then I might reference equation 3. So that's just the way I organize it. If you want to adopt that, you can. It's up to you. So I say we can use that table to keep things in order. Okay. Here's our first example. Hopefully now, with this example, you'll be able to get an idea of what we mean by the constraint. All right? Find the maximum and minimum of the function f of xy equals x squared plus 2y squared on x squared plus y squared equals 1. Let me do something. I feel like I'm really forgetting something here. I'm recording. My headset's in. It's on. I don't know what. Just seems like I forgot something very important here. What's that? Yeah, I'm on like the 5th revision of this whole thing up here. Okay, so first let's look at what this function is by itself, right? Just the function itself is just some paraboloid sitting out there, right? It's just a paraboloid. It's like a big old bowl. Now, if I ask you what's the maximum or minimum of that, it would be the bottom of the bowl, wouldn't it? That would be a minimum. We wouldn't have a maximum. That's not what's being asked, though. What's being asked is for us to find the maximum and minimum of this function if the x's and y's that we're allowed to plug in have to satisfy this equation. Well, what is this equation? It's a cylinder in 3-dimensional space, right? In 2-dimensional space, it's a circle, isn't it? So we're almost saying take that circle in 2-dimensional space, which is everything on the ground here, right? That's a circle on the xy plane. And imagine just taking just those points and plugging them into the function. So mapping those up into the surface. If you map those up into the surface, you get that curve on the surface, don't you? Yes? And now let's pull the surface out completely. And we'll even take the dome. Well, we'll look at it from the top so you'll be convinced that that kind of is the circle mapped up, right? And then we'll take the surface completely out. We'll take the domain out. And so really, that function constrained to that equation, x squared plus y squared equals 1, is really just this curve, isn't it? And we want to know the maximum and minimum values of that curve. So we want to know those points right there. Got it? That's the geometric interpretation of what we're doing. So now let's do it. So what I'm going to do is write down my function f of x, y equals x squared plus 2y squared. And my constraint. Now remember if you flip back to the note, the very first thing that I put up here, I'll flip back so you can see it. The constraint was of this form. G of xy equals k, where k is a constant here. So the g function is actually just the stuff with x's and y's in it on one side of the equation. That's your g function. The right side is your k. So when I come down here and I'm trying to write out what f is and what g is, I would put here g of xy is what? What's my g function? It is 1, but what's the function g? X squared plus y squared, right? That's what g of xy is. Now what's k? K is 1, right? That's the setup. Now let's set up the 3 equations that we're going to have here. Equation 1 is going to be the equation that the partial of f with respect to x must be equal to the lambda, partial of g with respect to x. That's my first equation. My second equation is that the partial of f with respect to y must equal lambda partial of g with respect to y. And then my third equation is the what? Is the constraint. X squared plus y squared must equal 1. Now let's go ahead and take some partials. We're just going to work this first equation down the left side. What's partial of f with respect to x? 2x. What is partial of g with respect to x? Lambda, then 2x. Agreed? Let's just get all the partials. Let's go to the next equation. What's partial of f with respect to y? 4y equals lambda. Partial of g with respect to y is 2y. All right, and then there's nothing to do on the third equation, right? So let's go back to the first equation. Clean things up a little bit here. I'll divide both sides by 2. Second equation, I'll divide both sides by 2 also. So what I need to do now is find an x, a y, and a lambda that make all three of these true simultaneously. So it's like a system of equations, isn't it? System of equations. The key here today is that we have a system of equations, but they are not necessarily linear equations. So you can't use a matrix, you can't do elimination or substitution or anything like that, you know, as far as matrices are concerned, because matrices work with linear equations only. These do not have to be linear. In fact, look at the equation 3. It's nonlinear, right? X squared plus y squared, so it's nonlinear. So we're just going to have to try and do it some other way. So let me work with this first equation. Do you agree that this first equation, I'm going to switch to blue because now I'm actually starting to work with it. I'm going to move all my x's to one side, or all my terms with x to one side. I'm going to factor out an x. And what does that tell me? Or x is 0. So this means that x is 0 or lambda must be equal to 1. So the only way to make equation 1 true is if you let x be 0 or lambda be 1, right? Fair? What about the second equation? Bring all the y terms to one side. Factor out a y. Which means that y must be 0 or lambda must be 2. So now we have to very carefully work through this, all right? I'm going to work to try and keep everything on one page. I'm going to work in this space right here, all right? Try not to clutter up equation 3, but only because of space I'm going to be over here. Normally I just keep working down below this. Let's try and force the first equation to be true. So we can have one of these two things happen, right? So I'm going to put here, suppose x is 0, right? This is the way we write suppose. Have I shown you all that before? Okay. That's a capital S with this little line. That means suppose. Suppose x is 0. Right? Then, if x is 0, what other information can you tell me? Y is plus or minus 1. From where? Equation 3. So what I put here, suppose x is 0. Then, equation 3 implies that what y squared must be 1, which means y must be plus or minus 1. Agreed? Now, x was 0, wasn't it? We satisfied the first equation. Y is plus or minus 1, which means we satisfied the third equation, right? But have we satisfied the second one? No. So what must we do to make the second one true right now? Can you let y be 0? No, we just said y was plus or minus 1, right? So the only way to get y to be 0 would be to do, second equation be true would be to do what? Let lambda be 2. Now, is lambda being 2 going to affect equation 1? No, because we took this case only, right? We took the case that x was 0. So if x is 0, this is satisfied. Lambda doesn't matter here anymore. X being 0 forced this equation to generate a y being plus or minus 1. And now to satisfy the second one, that forces our hand to make lambda 2. Y'all see that? You have to be real careful with these things because they all affect each other. You can't just be like solving and get an answer and not understand where it comes from, what it means. So here's what I've got. I'll just put here, and equation 2 implies that lambda must be 2. Again, because y can't be 0, right? We've already established y. So here's what we have. The point we have, remember it said you have to find x, y, lambda that satisfy all three equations. I know that 0 for x, plus or minus 1 for y, and 2 for lambda. X, y, lambda. Now don't look at this as like x, y, z. I'm just giving you an ordered triple, but it's not a point we're plotting or anything. It's just the x-coordinate, the y-coordinate, and then the lambda we were looking for. That will satisfy all three, correct? Is that the only way it could happen? This is what makes the Lagrange challenging, because you think you have an answer, you think you're done, but there's more. I did that by letting x be 0. How else could I satisfy equation 1? So I'm going to box this up, and now I'm going to come in here, and somewhere else on this page I'm going to put suppose lambda is 1. If lambda is 1, what is that force? You got equation 1 satisfied, right? But the only way equation 2 can be satisfied is if y is 0, lambda is 2. But I already said lambda is 1, so lambda can't be 2, so y must be 0, right? So then equation 2 implies that y must be 0. But because y is now 0, equation 3 forces us to have x be plus or minus 1. And equation 3 implies that x squared must equal 1, which means that x is plus or minus 1. With me? So tell me what the ordered triple here is for x, y, lambda. Plus or minus 1, 0, and lambda was 1, right? All right. Is that it? Well, yeah, let's go look at equation 2 now. How could we get equation 2 to be true? Let y be 0. But wait a minute. If y is 0, we already know what x has to be, plus or minus 1, right? And if y is 0 here, then could you also have x be 0? No. You can't have x and y both be 0, could you? Because then you couldn't, your third equation wouldn't be satisfied, would it? Right? This equation wouldn't be satisfied? I cannot let x and y be 0 simultaneously, because that one wouldn't work. So if I let y be 0, that forces x to be plus or minus 1. But I already looked at that, didn't I? We just did that? Whoa. We just did that right here, right? Y was 0, x had to be plus or minus 1. So we already know what happens there. What if lambda is 2? We did that, right? But that was because, look, forget we did this for a second. If lambda is 2, then what has to happen here? X is 0, and then we go back to the same argument. So that's it right there. These are 4 points, aren't they? So to find the max and min now, what I do is I take these points and I plug them into the function. Now, we don't need to consider the lambdas. The lambdas were just part of Lagrange's method. The x's and the y's are what we plug in. So what we want is this. I want to know what f of 0, 1 is, f of 0, negative 1, f of 1, 0, and f of negative 1, 0. Figure out what those are. The biggest is where you have a max, and the smallest is where you have a min. So I forgot the function. X squared plus 2y squared. So what do you get if you plug in 0, 1? 2, 0, negative 1? 2 again, right? If you plug in 1, 0, 1 and negative 1, 0 gets 1 again. So you could look at these now as ordered triples that are on our graph. That's x, y, z. X, y, z. X, y, z. X, y, z. So what is the maximum value? 2. Where does it happen? Well, it happens at 2 different places, right? What's the minimum value? 1. Where does it happen? At 2 different places. So if we go back to our graph, where was our max? Where did we have our max? At 0, 1. So this must be my y-axis here, right? X is 0, y is 1. We come up to 2. Y'all see it? Okay. We good enough to move on to the next one? The algebra in this one was very basic, nothing fancy here. Now I want you to see the difference between that problem and this problem. Very similar though. Find the maximum and minimum values of f of x equals x squared plus 2y squared. Same function, right? Same paraboloid. What's different though? Our domain, right? That constraint is actually not an equation, it's an inequality, isn't it? So that's actually a disk, not a circle. So do y'all see what the difference is as far as the constraint? Like with the circle, we plugged in all the edges of the circle, all those points up, and it mapped to a curve, didn't it? What's going to happen when I constrain it to a disk? Take that disk on the ground, right? Take that disk, just map that disk up into the function. Take out the function. Take out the domain. We'll take the function out completely. And now you have a surface, don't you? Now there's certain parts of it are the same, aren't they? What's still the same? Those two maxes, right? Those two mins would still come from Lagrange. But those two mins are no longer our mins because you can now include this point on the bottom. So how do you think you find the point on the bottom? Well, isn't that point on the bottom, wouldn't we have gotten that if we had just looked at the surface without restricting it? Wouldn't we have got that by computing capital D from 11.7? That's what you would have to do here. You would actually have to go compute capital D and find any local maxes and local mins. So I'm going to do that quickly. We've already done the edge of the circle, right? We just need to do the interior of it. Let me get to a new page here. So in this example, f of x, y, I'm going to move real quick through this. X squared plus 2y squared on x squared plus y squared less than or equal to 1. The first thing I'll do is I'll look at it as if this wasn't even here. Okay? Forget it's even there. And let's go find D. So how do we find D? We need partial with respect to x, which was 2x. Partial with respect to y, which was 4y. Then you take those partials and set them equal to 0. Those are easy to solve, right? When is that 0? That means x is 0. And this one, at y is 0. And that's the only way it can happen, right? So we have this point 0, 0. That's our critical point. We need to compute D at that critical point. Yes? But do we really need D? I mean, think about this. Do we really need to know if it's a local max or local min? No, because all that point tells us is it's a place we need to look, right? Something important is happening there. So now what we would do is we would stop and we would go along the edge of the circle. How would we go along the edge of the circle? Lagrange. Lagrange would supply us those 4 points, right? Remember we tested all those points? But now we would include with those points what? F of 0, 0, and if you plug that in, you get 0. So now the two points that gave you 2 are your max points, right? And this point is now your min. So those other 2 that we found, they're not part of the answer. Does that make sense? Okay. So this would be your min. And then your f of 0, 1, f of 0, negative 1, those were equal to 2. Those would be your maxes. See previous problem, right? We just did that. See previous. So that was just to show you that we can still find max and mins on things other than curves. We can still include like nice regions in our domain. Questions? Still haven't figured out how to not lose that. Did y'all have a good break? Happy to be back? Oh, shit. Okay, how about this one? Find the maximum minimum of f of x equals 4x plus 6y with the constraint x squared plus y squared equals 13. So when you look at this 4x plus 6y, this really is like z equals 4x plus 6y, which is a plane. Okay? Surface-wise, it's a plane. There it is. And we have a constraint, which is a what? Circle. So there's our domain on the ground. When we plug that domain into the plane, we get this. Right? It appears that we should have a single max and a single min, right? See if we can find them. The partials are going to be pretty clean, aren't they? What's our g of xy? X squared plus y squared again. K is 13. All right. Equation 1 is 4 equals lambda 2x, or 2 lambda x, or 2x lambda. It doesn't really matter how you write it. Normally, it's really bad notation to put the 2 in between the two variables. I'm only doing it to stress that that's lambda times the partial of g with respect to x. Okay, what about our next one? 6 equals lambda times 2y. And our third equation, x squared plus y squared is 13. All right. Divide the first equation through by 2. Divide the second equation by 2. Any ideas? Solve for x in the first equation. So how should I solve for x? Divide by lambda. 2 over lambda is x, right? But you can only do that, what? If lambda is not 0, right? If lambda is not 0. With lambda not being 0, I'm just going to put that next to it. But if lambda is 0, what can you tell me about the first equation? If lambda is 0. It can't be true, right? So lambda won't be 0, but we need to keep that in mind, because on the problem later down the road, lambda being 0 could still maintain equalities up there, and we have to consider it. So we would have to look at, this is what we do if lambda is not 0, and what if lambda was 0? And we would have to look at that scenario. Okay, so as long as lambda is not 0, that's true. What about the other equation, equation 2? Same thing, right? Now, I don't need to necessarily say lambda is not 0, but I'll put it next to it, lambda not 0. Okay, anything else? What else do you want me to do here? Now take those two, you know what x is, you know what y is, and take them and plug them in here. If you do that, you're going to have a single equation with just lambda in it, right? Okay, so let's plug it in. So if we take this and this, and we plug those into equation 3, we get 2 over lambda squared plus 3 over lambda squared must equal 13, right? Square each of those. 4 over lambda squared plus 9 over lambda squared equals 13. Which means that they have the same denominator, right? 13 over lambda squared equals 13. Multiply both sides by lambda squared. 13 equals 13 lambda squared. Divide both sides by by 13, get 1. Square root of 1 is plus or minus 1. So lambda can be what? Plus or minus 1. Questions? Now, lambda being plus or minus 1, what of those equations does it satisfy? If lambda is 1, right, and this is x, and this is y, then that's satisfied, right, the third equation? But we need to figure out what would x be and what would y be if lambda was 1 and if lambda was negative 1, right? So what would happen if lambda was 1? X would be 2 and y would be 3. So here's one of my points that I'm going to be looking at. X is 2, y is 3, lambda is 1. X, y, lambda. What's another one? Negative 2, negative 3, negative 1. Y'all see where those come from? Okay, is that the only possible way that we can make the equations true? Did we miss anything, I guess, is what we need to be careful with here. We decided to take these equations and solve for x and solve for y, right? Yes? Why not solve for lambda in each of those? Could you? And then set them equal to each other. So solve this first one for lambda, and what would you get? I'm going to have to start a new page. We had 2 equals lambda x. We had 3 equals lambda y. If you solve for lambda, you get 2 over x equals lambda as long as what? X is not 0. And solving for lambda here, 3 over y equals lambda as long as y is not 0. But that's okay because x and y both can't be 0 at the same time, right? Because then your third equation wouldn't be true. Now set them equal to each other and you get 2 over x equals 3 over y, correct? So 2y equals 3x, or y equals 3 halves x. So what? What could I do with that? Go to the third equation with that, right? I could have gone to the third equation, and it would have been x squared plus y squared, but what's y? 3 halves x squared must be 13, which means x squared plus 9/4 x squared must be 13. Get a common denominator. 4/4, add it. Once you get 13x squared over 4. Y'all with me or not? 4 on top, 4 on bottom. Put them together. 13 over 4x squared equals 13. Multiply both sides by the reciprocal of 13/4, so 4/13. You get x squared is what? 4, which means x must be plus or minus 2. And now you can figure out what y is, right? Did we get that earlier, though? We did, didn't we? So let's see. What if x is 2? What would y be? What would y be? It'd be 3. That's going back to this right here. And what would lambda be? Would it check? If x is 2, lambda is 1. If y is 3, lambda is 1, right? So lambda would be 1. Now what if x was negative 2? What would y be? Negative 3? And what would lambda be? Negative 1. Isn't that the same exact thing we got a second ago? Isn't it? So I guess what am I saying here? This would have been enough, is what I'm trying to say. This would have been okay. The reason I showed you the other way is because what if I would have chose to solve for lambda instead of solve for x or y? Either way works. And that's going to be part of the challenge for you in the next couple of problems, is that sometimes you don't know, do you solve for lambda, do you solve for x? Like what algebra technique do you throw at it? And some problems are a little easier to do one way than the other. So you just have to play with it. So we still need to figure out which of these gives us a max and min, right? So I'm coming back here. Let me go ahead. Let me go f of what? What am I plugging into f? 2, 3, and also negative 2, negative 3. So what do I get if I plug in 2, 3? What's that? 8 plus 18, right? 26. I'm plugging it into 4x plus 6y, right? What do you get when you plug in negative 2, negative 3? Get negative 26. So we have an obvious max and an obvious min here. Questions? May I proceed? All right, let's get back to this now. Find the max and min of f of x y equals e to the xy. Now we're starting to get some more interesting functions here. With the constraint x cubed plus y cubed equals 16. What I've done here, I've kind of changed things up a little bit to help us see things. I put the constraint equation as if it's like a curve on the xy plane. So just graphing that in the xy plane. So if we take just those points, take those points and map them up into the surface, what would we get? Well, here's the surface. It's kind of a weird looking surface, right? So let me show you the domain on the ground there. See the domain coming across there? Map those points up into the curve. You get that black curve there. And what we want are the max and min points. It appears that we are just going to get a max and that there will be no min. So we'll have to see if we can get that result. All right? So f of xy equals e to the xy. G of xy is x cubed plus y cubed. And k is 16. Okay, what does my equation 1 look like? Really, it's just, it'll be part of that third equation. But the thing is, you have to separate g from the constant. So the g is the part that has the x and y's in it. That's all we're interested in, really. But we'll use the 16 later on in the equation 3. So, and you could actually bring the 16 over and make it part of g, make it a negative 16, and then k would be 0. But we just have to be able to separate that g is not an equation, g is a function. All right, so equation 1 is going to give us, what's the partial of f with respect to x? Y e to the xy. That must equal lambda. What's the partial of g with respect to x? 3x squared. That looks a little more interesting, doesn't it? That's going to be somewhat challenging, maybe. Okay, now what's equation 2? x to the e to the, or x times e to the xy equals lambda 3y squared times 3y squared. And then we have our constraint equation, which is x cubed plus y cubed equals 16. Shit, right? Look at this thing. What do you think? Solve for lambda, then equal to each other. That's one approach, right? Solve for lambda, set them equal to each other. What would be, is there, I mean, could you solve for y in the first one? Not really, because you have this, right? You could solve for x squared, right, by dividing through by 3 lambda, but then you still have x up here also, right? You see that we've totally turned up the level here on the algebra required. So solving for lambda looks like a possibility, and then setting them equal to each other. The reason why that looks preferable is because I can get lambda by itself, right? I cannot get y by itself without it still being in terms of y, right? Because the y lives up here. Here I can't get x by itself because x still lives up here. So let's try the lambda. Let's see what happens. Solve this first one for lambda. I get y e to the xy over 3x squared equals lambda, but I need to tell myself I can only do this as long as what? X is not equal to 0. And then on the other one, same thing. X e to the xy over 3y squared is equal to lambda, so long as y is not 0. I'm not too concerned about x and y being 0. Why? Third equation wouldn't allow that to happen anyway, right? X and y couldn't both be 0 simultaneously. So let's see here. Set them equal to each other. You get y e to the xy over 3x squared equals x e to the xy over 3y squared. And what about the e to the xy's? Cancel out. You basically divide both sides by e to the xy. Since e to the xy can never be 0, you don't have to worry about division by 0 there, right? You just cancel them out. Then you can like cross multiply almost, right? And you get what? 3y cubed equals 3x cubed. Like multiplying cross kind of. Divide by 3. Y cubed equals x cubed. And what does that mean? X must equal y. Not plus or minus because those are odd powers, right? So you take cube roots, you don't do plus or minus on cube roots. Cube root of both sides. So I know that in order for those equations to be true, they must, x and y must be the same, right? But I also must satisfy equation 3. So let's go to equation 3. If I let my, let's say I'm going to replace my y with x, then it becomes x cubed plus, instead of y cubed, x cubed again equals 16. And that means that 2x cubed equals 16, which means that x cubed equals 8, which means x is 2. But if x is 2, what's y? Y is 2 also. Agreed? All right. So, what's lambda? What's lambda? Because remember, I need a point. So I'm saying x is 2, that means y is 2, but what's lambda? Oh, well, I mean, it's kind of nasty, isn't it? It's 2e to the 4th power over 3 times 2 squared, so 4, and those cancel. So what is it, like e to the 4th over 6? And lambda doesn't really matter. It doesn't factor into anything. It's just that you have to solve all three. The power of lambda is that it gives you a third variable to work with the third equation. If you only were trying to solve two equations with two variables, sorry, three variables without a third equation, you wouldn't be able to do it. So we need the lambda in here. I'm just going to put it, it's e to the fourth over 6. But the key points here are the 2 and 2. Now we've missed something. What have I missed? How about, I said that x and y could not be 0 simultaneously, right? Right? If x was 0, this wouldn't have worked, right? So let's just ask ourselves, what if x is 0? What if x was 0? What would this equation turn into? 0. I'm going to write this down. I don't want to think through it. Let me now suppose, I'll do it in green because this is kind of a different thought I'm having here now. Suppose x is 0 and y can't be, right? Because if they're both 0, equation 3 is done, right? Can't have the equation 3. So let's say, what if x was 0 but y wasn't? What would equation 1 tell us if x was 0? Go to equation 1, replace x with 0, and you would get what? Y times, what's e to the 0? 1. And you get y equals 0. Equation 1 would tell me y equals 0, which is a contradiction to what I assumed. Have y'all ever seen that before? Y'all seen the arrow? That means that this, like, P kind of implies Q. Like, this happens, then that happens. That's the result. That symbol I just drew there are two arrows going head to head to each other. What it means is that I assumed x was 0 and y wasn't, and then my conclusion was that y had to be 0. So I have one thing saying y can't be 0, the other one saying y is 0. It's a contradiction, and therefore it can't happen, and therefore I don't have to consider that. But I had to consider it. You know what I'm saying? Like, I had to consider it and come to a contradiction. Because in some problems you consider it and it actually leads you to more answers. The biggest problem I see on tests and problems with this, like even on take-home, is that students don't test every scenario. So the ones you do are correct, but you're missing others because you haven't looked at every possible case. Okay. We know that that made sense because we only had one answer because of the geometric picture I gave you. But if I hadn't given you that, you would have no idea that there's only one answer. Now, how do I know this is a max or a min? So, but I'm only plugging one thing in, right? F of, what, 2, 2? What happens if I plug in 2, 2? I get e to the fourth? How do I know that's a max? You could find D, but you don't even have to work that hard. You know it's either a max or a min, right? You know that much? Plug in a point around it. Plug in something around it. But it has to be a point that lives on our constraint, right? Because we're constrained to that equation. So somebody give me a point that lives on the constraint. Remember, this is an equation, g of x, y equals 16. Can somebody give me any x and y that satisfy that equation? Don't think too hard about it. You could use something complicated, or you could just use 0, 2. Wait, no, oh, wait, cube root, sorry. Say again, that's what you were saying, right? Cube root of 16 plus 0, yes. That'll work. You want to use that? So let me test. Did we have an 8 in the previous problem? I don't know where 8 came from. It was like in my head there. Yeah, I don't know where that came from. So let's test the point that had to live under the constraint, which you said cube root of 16, 0. Plug it in. Plug it in where? Into the function, right? And what are we going to get? It's e to the 0, isn't it? Because you multiply x times y, and you get 1. What's bigger, e to the 4th or 1? E to the 4th. So that means that I know e to the 4th was either the highest or lowest point. I picked some other point that lived on that restricted domain and found that it was smaller. So that means that every point around it's smaller. So that means this is a max. Got it? Questions? How does this look to you all so far? All right. Yeah, we'll have some cheat sheet on there. Something. So, I'll let you have an additional one so you don't have to recreate it. So you can have a second one. But we still don't even know what the final is going to cover. It might only cover from today on. So, okay, I worked this all out, didn't I? I already did this already by hand. Yeah. So I think I do the next one by hand also, right? So instead of me writing it all down, I'd like to walk through this one with you. So here's the function, right? Here's our function, 1 over x, 1 over plus 1 over y, and then here's the constraint. We've got a geometric picture of this. There's the domain on the ground. Take all those points, map them into the curve. Take the curve out of here. Take the domain out of there. It's really difficult to see what's happening on this thing. So if you take the answers, looks like we're going to have 1 max and 1 min. See it? And what is this? Nothing, I guess. All right, so how did I do this? First, we set up the equations, right? Equation 1, equation 2, equation 3. Those are just partials, right? Then solve equation 1 and equation 2 for lambda. So how did I get x over 2 for lambda on this one right here? Just multiply both sides by x cubed, divide by -2, right? Now, I didn't put it on here. When you multiply both sides by x cubed, x can't be 0, right? Because you can never multiply both sides of an equation by 0. It just wipes everything out, and then it's like, why did you even do that? So, but I get this lambda is this and this. Set those equal to each other, we get x is y. Pretty much like we just had a second ago. Now plugging that in to the third equation, which was this one here, with equal to 1, you get x is equal to plus or minus root 2, which means that y is equal to plus or minus root 2. So they're both either root 2 together positive, or they're both negative root 2s. Plug them in, you get max, you get min. Does that make sense? I went through that pretty quick, but I mean, it's all written out there for you. You can go back and look at it. Okay, that's Lagrange 2 variables. 3 variables is just a simple extension. It's the same 2 equations. Gradient of f equals lambda gradient of g. Second condition is that the g of x, y, z is equal to k. So you see, we just have functions of 3 variables now instead of 2. So what are we going to lose here when I try and explain what this is? What am I going to lose in this now that we've gone to 3 variables? I'm not going to be able to draw a picture of a surface in a restricted domain and map it up into the surface. We can't do that because our domain is actually in what space? 3D, and our function's in 4, right? So we can't visualize this, but we can still do the same thing, right? This is what we were talking about earlier. You have a function of however many variables you want, 20,000 variables. Then to find optimum solutions, you just take the gradient, set it equal to lambda the gradient of the other. Doesn't matter how many variables you have. But then you have a system of 20,000 variables, maybe nonlinear equations, and you have to have a computer help you solve those systems of equations, right? Imagine having 20 variables. So you have, 20 equations that you have to satisfy. You don't want to do that by hand. In fact, you probably couldn't, and I couldn't either. It would just be something you throw a computer at, and you just let it go. But then you have to know how to write the code to make the computer do it without making errors. So anyway, it's called numerical analysis. There's a whole process of learning how to code a computer correctly so it doesn't make mistakes. All right, let's do this. Gradient f equal lambda gradient g means that those partials have to be equal to lambda times those partials, which means we have 3 partials now, right? Which means we have 3 equations, and then we have a 4th equation given to us by the constraint. So now we have 4 variables, right? X, y, z, and lambda. We have to solve 4 variables. We have 4 equations. Friggin' sounds fun, doesn't it? I don't work these out, do I? No, I don't. Find the maximum, minimum values of these. I'm going to do both of these, even though I don't think I need to. I will do them both. I think I can work through the first one pretty quick. So we have the function f of x, y, z equals 8x minus 4z. My g of x, y, z equals, seriously? X squared plus 10y squared plus z squared. What's my k? 5. All right, equation 1. 8 equals 2 lambda x. Second equation. 0 equals 20 lambda y. Third equation. Negative 4 equals 2z lambda or 2 lambda z. Fourth equation is that thing up there, right? X squared plus 10y squared plus z squared equals 5. Remember, this function here, f of x, y, z, the f function, lives in 4-dimensional space, right? But you're only allowed to plug in values that come from this restriction. What is x squared plus 10y squared plus z squared equals 5? Isn't that some sort of like ellipsoid or something? Almost looks like a sphere, doesn't it? So it's like you're only allowed to take points on the surface of an ellipsoid and plug those into this function. It spits out something in 4-dimensional space. And what's the greatest and smallest value? So, all right, any of these equations look fun? I think equation 2 gives us immediate results, doesn't it? Equation 2 tells us that what? Lambda must be 0 or lambda must be, or y must be 0, right? That gives us a starting point, doesn't it? That's the only way I can get that second equation to be true. So let me start with that. Let me start with lambda being 0. Suppose lambda equals 0. Then equation 2 is satisfied, right? What does equation 1 tell us? 8 equals 0. Which means that, that's a contradiction, which means that lambda can't be 0, right? So we're done. We do not even consider that. So now we have to suppose something else. Y equals 0. Isn't this the only, these are the only 2 ways I'm ever going to get the second one to be true. So y equals 0, I'm down to this last hope here. If y is 0, what can I work with? If y is 0, does that give me any information? Well, Well, not really, right? I mean, it's different ways of looking at it. It does give me something, right? Y is 0. Which in the fourth equation, if y is 0, it reduces the fourth equation to an equation in x and z only, doesn't it? And then I can go back and do what I did earlier in the previous problems, where maybe I could solve this one for x and this one over here for z, and then plug those into that one and get x and z. You know what I'm saying? So we're on the right road here. I'm going to say that from this, equation 3 gives me x squared plus equation 4. Thank you. Equation 4 gives me x squared plus z squared equals 5. That doesn't really help. But if I take equation 1, what do you say we take equation 1 and we solve it for x? What do we get if we solve it for x? 4 over lambda. As long as lambda is not what? So I'm going to have to remember to come back and consider what if lambda was 0. But it's going to be a real quick consideration, isn't it? Oh, we did it here. Yeah, sorry. Spring break was too good. All right, equation 3. What does equation 3 give us? Z is negative 2 over lambda, correct? And now go back into equation 4. What's x squared? 16 over lambda squared. Plus what's z squared? 4 over lambda squared. That must equal 5. 16 plus 4 is 20. Multiply both sides by lambda squared. Divide by 5. 4. Lambda's plus or minus 2. Once I know lambda, I can go get x and y, can't I? I mean, x and z. I already know what y is, don't I? So let's try these. Check this out. This is the way I'm going to write it. I'm going to have x, y, z, lambda. So we said lambda being 2. I already know y is 0. If lambda is 2, what's x? 2. What's y or what's z? I'm working right here. Lambda was 2 or negative 2, right? If lambda is 2, x would be 2, right? And then z would be negative 1. And I already know y was 0, because that was my original assumption. Scroll up. Yes? Okay, so what was the z was negative 1? Now, I also have to let lambda be negative 2, which would have given me negative 2, 0, positive 1, right? So if lambda is negative 2, that becomes a negative 2. Negative 2 here becomes a positive 1. Y is still 0. That was my original assumption. Yes? Are we missing anything? Hey, look, you have to satisfy all 4 equations, right? The only way to satisfy equation 2 was to let that happen. Those 2 things. We tried to let lambda be 0. Nothing came of that. The only other way was to get y to be 0. So now whatever happens with the other 4 equations doesn't matter, because that's the only way to get the second one true. That's it, right? All right. Well, you have to be convinced that you've looked at all scenarios. I mean, fortunately with this one, we were reduced to two cases. So once we looked at both of them, we're good to go. We still have to evaluate the function, don't we? F of 2, 0, negative 1. F of negative 2, 0, negative 1. And we should get, one of these was a max and one's a min. Right now, it's nothing that we can really visualize. You know, remember in the previous problems we had the domain was something on the ground that got mapped into a surface, and we were looking at height, right, up and down. Now our domain isn't something on the ground. Our domain is something in three-dimensional space, and that's getting mapped into a function that takes it into a fourth dimension. And we're just looking at whatever that comes out as a number. What's the biggest? What's the smallest? It can. You could look at the surface of the Earth, and you could look at, you know, restricting the surface of the Earth to, let's say, the northern hemisphere, and the function is just the temperature at each point. So you plug in a point on the sphere that's three-dimensional, goes into a function that spits out the temperature at that point. So this would represent the maximum temperature on that northern hemisphere. So it can have value, it can have some sort of quantity to it. Just depends on what the function is. Did y'all plug those in? 16, is it what, 20? And negative 20. Max and min. All right, let's look at example 6. Man, I'm down to 20 minutes. I think I might just set this one up. I don't know if I'm going to work through this whole thing, because I want to show you something else we can do. There's the way it's presented to you. What's equation 1 here? Two x y squared z squared, because it's all multiplication, right? Equals lambda 2x. Next equation. 2x squared yz squared equals lambda 2y. Third equation. 2x squared y squared z equals 2 lambda z. And then the fourth equation is what we have up here, right? Yeah, I have to work through this one. This is a really cool technique to get this one. It's hard to solve the first equation for x. It's hard to solve it for y. It's hard to solve it for z. You could solve it for lambda, couldn't you? Yes? Then you could solve this one for lambda and that one for lambda. Then you could set all three equal to each other. Turns out that could be done. It's really a nightmare, though. So watch this instead. What I'm going to do is I'm going to recognize that these three pieces here are really similar to each other, aren't they? They're all almost 2 and then each variable squared multiplied, right? Except the first one's missing what? X squared, right? This one's missing the y squared, and that one's missing what? Z squared. So what I'm going to do is very tricky. I'm going to take this first equation. I'm going to multiply both sides of the equation by x. Now, isn't the left side 2x squared, y squared, z squared? Now, in the second equation, I'm going to multiply both sides by y. And on the third one, multiply both sides of the equation by z. Yes? Now that means that this has to be this, which has to be this, which has to be this. So can't I set those three pieces equal to each other now? Can't I? They're all the same. So I can set this, this, and this equal to each other. So I know that 2 lambda x squared must be equal to 2 lambda y squared, which must be equal to 2 lambda z squared. Now I did assume something when I did this. Right? When I multiplied both sides by x here, I assumed x was not what? And then y was not 0, and z was not 0. But that's kind of assumed again, because up there in our equation 4, you couldn't have them all be 0, could you? But we'll keep it in mind. Let's get rid of the 2's. Can I divide by lambda? Yes, I can. As long as what? Okay, so this means x squared must equal y squared must equal z squared as long as lambda was not 0. And if x squared plus y squared plus, if x squared is equal to y squared is equal to z squared, then the fourth equation would give me what? Let's just make them all x's, right? That would give us x squared plus x squared plus x squared equals 1, which means 3x squared would equal 1. So x would be equal to plus or minus 1 over square root 1 over 3. Make sense? Now you can figure out what y is and what z is. You'd have to look at all the different scenarios. Positive x, negative y, positive z, positive x. Wait. For example, you would have to look at this. Square root 1 over 3, square root 1 over 3, square root 1 over 3, and then you'll have your lambda, whatever lambda is, right? Then you'd have to go, minus on the second one. Then you would have to do minus on the third. Pardon me? Positive, but you're squaring them. So I believe there's like 6 different variations you could do, right? You have to do plus and minus on each of these, right? So you could have the first one plus, these two minus, this plus, this minus, this minus, this plus, and then do the same thing with this one minus, plus, plus, minus, minus, plus, minus, minus, plus. All those different combinations. You'll probably get a lot of overlap. Well, I don't know. It depends on the original function, though. Yeah, see, it won't matter because the original function, everything's squared, so it won't matter. But that would have to be established. Those 6 points would have to be established. Now, we did not look at, we said this is all if lambda was not 0. What if lambda was 0? If lambda was 0, what would happen here? 0, 0, 0, which means that this, and this would all have to be equal to 0, which means that x would have to be 0, or y 0, or z 0. What if x was 0? What if x was 0? Would this be true? Remember, lambda is 0 right now, right? What if x is 0? Is this true? And lambda is 0 here, so this would be true also, wouldn't it? And then lambda is 0 here, and x is 0, that would be true also. So all three are true, right? If lambda is 0 and x is 0, they're all true. Regardless of y, regardless of z. But what? Well, that was here, right? That's if this, remember I said this would be true as long as x is not 0, y is not 0, z is not 0. So I'm just saying forget this, forget everything we did pretty much. Come down to this right here. This is where we said lambda couldn't be 0, came from this. Okay. If lambda was 0 right here, these three would be satisfied. Yes? With x being 0. But this lambda not being 0 came from the assumption that these would all be the same. So you can't force x to be 0 and let y and z be free, because this says that this is the relationship between them, right? Only if lambda is not 0. Because remember, we divided by lambda here, everyone, right? I want you to think about this a little more. Convince yourself whether or not you've looked at all possibilities. Because what I'm asking you to do is this. Let me erase some of this here. Just look at that line right here. Look at this. If I tell you right now that x is 0 and lambda is 0, do you have equality in the first three equations? Yes? But then, you know, what about y and z? Then they could be whatever they want, couldn't they? If I let x be 0, lambda be 0, then my y could be anything, because these are all dead, right? This is 0, 0, 0, 0, 0, 0. So the equations are true. But we have to satisfy the fourth one, right? So if x is 0, what do you have? A circle, don't you? So every point on that circle satisfies the equation. Do you agree? I want you to consider this some more, okay? And if anyone wants to discuss it more, I'm trying to undo some stuff here. Why can't I? It would be 3 circles, because I was only considering x being 0, right? Well, you have a circle. It's like a circle, or since we're in 3D, it would be like a cylinder in one direction. Oh, wait, no, x was 0. So we'd have a circle one way, circle the other way, circle the other. So in the planes, we would have circles. It's not a sphere because you're not considering one of the variables must be 0. Think about it. Think about it. Huh? That's right. You got it already. The point is that even though if x is 0, y and z can be free, the key is that the function, if x is 0, the function's value is 0. So even though there's all these points where you may have maxes and mins from Lagrange, the function itself tells you if x was 0, the whole thing's 0. Same with if y was 0. You can satisfy these equations, but your function's still going to be 0. So 0 is, you know, this function's value spitting out zeros is all that would ever happen in those cases. Good. Good recognition on that. Is that the max or min? So we have to go look at these too. But see, that's where I'm saying it would not have been enough for you to have gone here with these and been done. You would have had to have considered lambda being 0 and convince yourself that there are other possible solutions. In fact, infinitely many on these circles. So it can get a little weird. Man, 10 minutes, huh? Find the maximum volume of a rectangular box with no lid if it is to be made from 12 square meters of cardboard. What are the dimensions? So the idea here is that you have 12 square meters of cardboard, or wait, no, you have a box. Let me go with what they wanted. A box, right? Square, does it say square there? Rectangular box. Rectangular. So it has no lid on it, right? But it has a bottom. So we want to find the maximum volume so that the total surface area is 12 square meters. So what is the surface area of a box? Well, you have to find the area of all the sides, right, and the bottom. So let's label some sides. How about this is x, this is y, and why don't we call that z? So what's the area of this front face right here? X, z. What's this one over here? Y, z. The back one, x, z. The side one, y, z. And then the bottom, x, y. So that's your surface area, right? So I'm going to put here area equals what? 2xz 2yz plus xy. And what must that surface area be? 12. Okay? That's our g. Now, what is the function we're trying to find the maximum of? The volume. What's the volume of that box? X, Y, Z. So here's your f. Here's your constraint. Do you see that? So gradient of f equals lambda gradient g. You're off to the races. I'm not going to work it out, but you see how it's created? You can do that problem with Cal 1, but why? Well, but you would have in Cal 1, you'd have to somehow relate the variables. You would have to have, you'd have to now come up, you see in Cal 1, you can only do max and mins of functions of one variable. So the way we did it in Cal 1 was that we somehow got y in terms of x, and then somehow got x in terms, or here we'd have a z. So it'd be very challenging in Cal 1 to try and get this problem to work out. We could do that problem in Cal 1. It's just not as easy as it is now for us, because the partials are easy. It should work out pretty clean. So what about look at the next one. Find the maximum volume of a rectangular box with a double bottom if it is to be made of 81 square feet of cardboard. So the only difference in this problem is we have a rectangular box, right? Well, but I'm not saying that it doesn't have a lid. So it does have a lid. It's got a double bottom. Yeah. So it actually has two. So double bottom is going to mean it's got one of those, and then put another one on top of it. Make sense? And it has a lid. So you're going to have, we label it X, Y, Z. You're going to have 2XZ. That's the front side here and the back side, right? And then you're going to have the two sides, which are what? 2YZ. And then you're going to have 3, because you have the top, and then the double bottom, you're going to have 3XYs. Oh, yeah. And that must be equal to what? 81. And then, of course, your volume, which is what you want to find the maximum of, is your XYZ. So that's your F. That's your constraint equation. Yeah, I don't work those out, right? Yeah, I'll let you all do those for a bonus, but let's say you have to do them both. Yeah, that'll be a nice way of trying to make up for your test a little bit for yourself. Do next time, okay, beginning of class. All right, where else are we going here? Okay, I want to try and get to this next one. Find the point or points on the sphere, x squared plus y squared plus z squared equals 4, closest and farthest from the point 3, 1, negative 1. So what are we trying to find the max and min of here? Farthest, closest. It's a distance, isn't it? The distance from what to what? A point to another point, right? What one point that I'm given is what? 3, 1, negative 1. The other point has to live on this sphere, right? But in general, the point that I'm trying to find the distance to lives in three-dimensional space, so it has an x, y, z, doesn't it? The constraint is that it can't just be any point. It has to what? Live on the sphere. Do you see that? So what I'm saying is I want the distance between that point, 3, 1, negative 1, and some arbitrary point, x, y, z, with the constraint that the x, y, z has to live on the sphere. Do y'all see that or not? So what is my f function? It's the distance between 2 points, isn't it? What is the distance between 2 points? Square root of x squared, well, that distance between 2 points, right? It's the difference of the x coordinate, so I'm going to say x minus, what's the x coordinate? 3, right? Squared, plus the y minus, what's the y coordinate of this point? 1, squared, plus z minus the coordinate, but that's a plus, I mean minus, so it'll be plus. That's our distance, isn't it? That's the distance between some arbitrary point, x, y, z, and the point 3, 1, negative 1. But the x, y, z is constrained now to this equation. It has to live on that sphere. So do y'all see that, how that's going to work? This is your G here, and there's your F. Are there questions? Um, is that what, oh, you're saying distance between the 2 points? Perhaps, yes, that sounds right. But you're actually going to be able to tell me what the points are. Yeah. But you would then have to know the distance from, where's my picture? You're talking about the distance from here, this one, to this one, is the diameter. But it's not connected to the distance from here to here. Like, you still have to have that distance from there to there, right? I don't know if that makes sense, what I'm saying there. Right? Like this. Okay. Now, here's something I would recommend you do. We'll make that a bonus problem, part of the bonus. The answers, I believe, are there already. But here's something that that you should do. You may remember this from calculus 1. If you're trying to find the minimum or maximum distance between 2 points, you can look at the distance squared. To get rid of the square root, when you take the derivatives, it's easier. So whatever points give you the, what I'm saying is just look at your f as being not having the square root, and just work with f being without the square root. Do your partials, work with all that. When you get your x, y, z, lambda, figure out what they are, and when you plug those back in, just remember at the end to take the square root, because it simplifies your partial derivative extremely, well, it's an extremely good thing, right, to not have that square root in there. I know I'm out of time, but you had a whole week off, so let me show you one more thing. Where's my notes? Damn it. Why does it keep doing that? Because this is going to tie into the last problem on your mini exam, which we haven't talked about when that's due. Come on. Okay. 11.86. Look, we've already done Lagrange with 3 variables, right? 1 constraint. It is possible to have a function subject to 2 constraints. And if you do have 2 constraints, not only do you have a g function equal to k, you now have an h function equal to some constant. And in that case, you have 3 conditions which must be met. Look at the difference in this formula. The introduction of not just gradient f equals lambda gradient g, but now you have this new thing, plus mu gradient h. Then these two have to be satisfied. It turns out you have 5 frickin' equations. You have the gradient of f equals lambda gx plus mu hx. Gradient, right? Partial of f with respect to y equals lambda g mu h. I am not giving you an example of this, all right? On your mini exam, remember you're only supposed to do the first 4 and then on the mini exam, if you threw it away, you'll have to come get one from me. On number 8, for the mini exam is an example of a Lagrange optimized one function, two constraints. And I'm not going to do one in class. So I want to see if you can, now that you understand the necessary algebra, can you figure this out using this right here? And if you need help, come by and I'll be happy to help you. But the system of equations becomes pretty complicated. You have 5 unknowns, 5 nonlinear equations. At some point, the number of constraints would limit you down to having nothing possible. It's kind of like, y'all can go. If you're happy, you can leave. If you need the mini exam, you'll have to follow me to my office because I don't have one. Go back to the 2D case. Remember where we had like a surface up here? And we constrained it to, let's say, circle here? Well, what if we add an additional constraint that now it's, also got to live on that line? So now you've constrained it to those 2 points. Now let's say you have another constraint now that makes it have to live on, this line. Well, now it's not possible. So you have no possible solution. So there would be a point where the number of constraints would kind of wipe out anything possible. Does that make sense? Sure. Yes, you could. So it'd be possible to have more, but at some point there's a limit to it being practical. That you would what?